please.
Thank you. Well, good afternoon, everyone. I'm Eneriz, and I'm going to share our research line on the implementation of neural networks in FPGAs for sensor fusion applications. So, as you may know, artificial neural networks are basically nonlinear models that are inspired by biological systems. Basically, the model construction is based on an iterative learning process that makes the model learn features from the dataset, and that's what we call training. And they have become so popular in recent years because they have been successfully applied in fields such as computer vision, natural language processing, or audio signal processing. And this is because there are a lot of different architectures that allow us to address many problems. The multi-layer perceptrons, or MLPs, are the simplest architectures among the artificial neural networks, and basically they are based on fully connected layers, where the outputs in green are dependent on the product of a matrix of weights that are in orange, and the input values of the previous layer in blue, along with a bias term, which is in red. Then we have to apply an activation function, which is a nonlinear function, which grants the model its nonlinearity capabilities. There are several examples of activation functions here. For example, the symbol, the hyperbolic tangent, or the rectified linear unit. The convolutional neural networks, or CNNs, are a little bit more complex architectures, but still really basic ones. Basically, in this case, the input can be multidimensional, and you can find also different layers. For example, the convolutional layers, which are the most common layers on this kind of architectures, basically are sliding weight kernels across the inputs, generating each of the elements in the output. Then you have also pooling layers, which basically reduce the dimensionality by inserting key information or consolidating it. And also it's common to place on fully connected layers, the same we have seen before in the MLPs, at the end of the models to give the final outputs. So this is similar as the previous speaker have told us. In this case, artificial neural networks are also computationally intensive, and for these reasons, they have been traditionally implemented under the cloud computing paradigm. Basically, the idea is under this paradigm is to run them on data centers, and in this way you have to upload your input data to that data center and then download the outputs of your model to your application point, and in this way you need a constant internet connection to operate the model, which limits its applicability geographically. It increases the energy consumption, also amplifies the use of the bandwidth of that internet connection, and also it possesses potential data privacy risks if a third-party data center is used to execute your model. The alternative of this is to use the edge computing paradigm, which in this case basically is the implementation of your models next to the application in a small hardware, which is low power and also low end. Under this idea, you have to optimize really well your implementations, because the computational capabilities this kind of hardware have is really less compared with the data centers have. So, and this paradigm, you have to optimize really well your implementation, but you have the advantages of not depending on that constant internet connection. And for these reasons, we think that edge computing is the best solution when you need, for example, power efficient implementations, or maybe you want to be real-time responsive, or even if you have to secure the privacy because you don't have to upload it to data centers. These are the main logic platforms, ranging from the most general purpose and flexible ones, like the central processing units or CPUs, to the most flexible most efficient but specialized ones, like the application-specific circuits or ASICs. And in the middle, we can find the GPUs, which are the graphical processing units, and also the Field-Programmable Gate Arrays, FPGAs. It is common nowadays to implement neural networks on GPUs because they are flexible enough to support that wide variety of architectures we have seen before, and they also have a good parallelization capabilities. But in contrast, the FPGAs are more hardware-driven meaning that you have to define the hardware you want to implement, and in this way, the development for these platforms is more challenging. But they have superior parallelization capabilities because of this, and they also enable the use of arbitrary data types in both the floating and the fixed point representations. And for these reasons, we believe that the FPGAs are well suited for implementations that require also power efficiency, real-time responsive, or even ultra low latencies. So since they are not pretty common, I want to introduce them a little bit. Basically, they are reprogrammable hardware, meaning that you can build custom digital circuits inside of them. And for this, they are based on arrays of configurable logic blocks, which feature, for example, multiplexer, lookup tables, flip-flops, and also basic arithmetic blocks. And in this way, by interconnecting these components, you can build that custom digital circuit you want. This process of interconnected components is called configuration, FPGA configuration, also FPGA programming. And for this, you have to use hardware decision languages, HDLs, which are so low level, and this is what really hardens the development for these platforms. There's an alternative for this that is called high-level synthesis that allows you to program FPGAs from algorithmic descriptions. And this is what we are using to program our FPGAs for the artificial neural networks applications. We have also talked about data types. Here is on the top, there is a 32-bit floating point data type, and here at the bottom is a 32-bit fixed point data type. The floating point data types have better range compared with the fixed point, but they have less precision compared with the fixed point, meaning that the fixed point representation has better precision per bit with the same number of bits. And also you have to take into account the hardware you have to implement to do arithmetic operations with both representations. And the thing is that with the floating point representation, due to its nature, these hardware architectures are more complex, meaning that they cost more FPGA resources. For this reason, it's pretty common to use fixed point representation in FPGA design, and it is what we are using in our designs. This is a slide that summarizes the process to implement artificial neural networks on FPGAs using custom architectures and via the SLS tools. Basically, once you've got your model trained, you have to translate it to a C++ description, which is the description that is going to use HLS to transform it to HDL, because the HLS serves like that translator from algorithmic descriptions to hardware descriptions. Then with the HDL, you can generate the bitstem, which is the file that tells the FPGA how to interconnect its resources doing the FPGA configuration. The key step in this process is the conversion to the C++ description, because it really influences how your model is going to perform once implemented on the FPGA. And this process has been traditionally done manually, but there are some frameworks that try to automate the entire process, including the conversion to the C++ description. Some frameworks are the FPGA CoffNet framework, which is from the Imperial College, the HLS4ML, which is from the Fast Machine Learning Organization, and there is also a framework from Xilinx, which is the manufacturer of the FPGAs we are using, which is called FIN, but they are still under development, meaning that they only support the most basic layers. So this is the approach we are using for implementing artificial neural networks on FPGAs, and now I'm going to introduce the sensor fusion applications where we have tested this approach. We have worked with high quality detection, with mid quality detection, and we are working now with a brain-computer interface. Basically, all of these applications demand an edge implementation because they have demands of, for example, portability, battery energy efficiency, because they want to be battery powered, or even real-time performance. So in our work on high quality detection, we employed a data set of 16 metal oxide sensors when exposed to atmospheres that contain a mixture of two gases, methane and ethylene. And the idea here was to infer the concentration of these two gases over the time. For this, we employed a multi-layer perceptor of two hidden layers, and we implemented it with a fixed point of 12 bits in total, 3 of them dedicated to the integral part. And here in red, there is the response of the model once implemented on the FPGA, and in blue, there is the real actual concentration of methane, and in orange here is the actual concentration of ethylene. And overall, this model was implemented on the FPGA with a fixed point representation with an average error around the 2.5%. Then we move to a mid-quality detection problem. In this case, we work with a dataset of that captured the outputs of 11 metal oxide sensors when exposed to the atmospheres, where there were different beef cut samples, and the dataset also had the total viable count, the TVC, which is a microbiological indicator of the quality of the meat. In this case, the idea was to infer the TVC from the outputs of the metal oxide sensors. For this, we employed again an MLP of 2 hidden layers, and then we conducted a test to see which is the fixed point representation that best performed our model implementation. For this, we defined a figure of merit that took into account the average mean square error and the number of bits in the representation, and we got that the best candidate that was best performing is the 10-2, which is basically a fixed point representation with 10 bits in total, 2 of them dedicated to the integral part. And finally, we are working with a brain-computer interface. We are using the motor imagery paradigm, which is basically the detection of simulated movements that are meant but not physically done. And for this, we are processing electrophalograms, EEGs, with up to 64 electrodes. This is the network we are using. It's a convolutional neural network that is called EEGNet. And since it's bigger than the MLPs we have been working with, we decided to parameterize its input in order to control the size of the entire network. And in this way, we are controlling the cost it has on the FPGA resources once implemented on the FPGA. We have three different parameters: T, which is the input time window; DS, which is the downsampling factor; and the number of channels, which up to the moment has been fixed to 64, but we have plans to reduce it. So this is the distribution of the FPGA resources and the latest across the different combination of the reduction parameters. And we decided to implement the model in both, which is the bigger model that fits in our FPGA, using a fixed point representation of 16 bits. And we decided to compare, in order to measure how well it's performing our implementation process, we decided to compute the difference between the accuracy after the model has been trained and after the model has been implemented. And the difference is around the 0.11%. So our implementation process is not really affecting the accuracy of the model. So just to sum up, we have seen that some applications may require edge implementations, and for these reasons, we believe that FPGAs are good candidates for this because they have superior parallelization capabilities, and they also enable the use of arbitrary data types. And we have seen also that the HLS tools can ease this process of implementing neural networks on FPGAs because they allow us to program them from C++ code. And finally, we have exemplified with this process with 3 different sensor fusion applications. Thanks for your attention, and if you have any questions.